In this video, we are going to discuss matrices, SAQs, exercise 3E, section 2, third problem. If A is equal to matrix 3 minus 3, 4, 2 minus 3, 4, 0, minus 1, 1, then show that A inverse is equal to AQ, which is also a very important problem. So now how to find A inverse is equal to AQ? So actually from the given matrix A, finding A inverse is equal to A is one method. Given that capital A is equal to 3 minus 3, 4, 2 minus 3, 4, and 0 minus 1, 1. See, finding A inverse and inverse of matrix A and finding AQ, that is one method. Now here I am telling the alternate method. So what is that? Given matrix A, this is 3 minus 3, 4, 2 minus 3, 4, 0 minus 1, 1. Now to show that required thing, what I am doing is finding A square. So what is A square here? A into A. So what is the matrix A here? So 3 minus 3, 4, and 2 minus 3, 4, 0 minus 1, 1. So into the matrix, same matrix again, 3 minus 3, 4. So 2 minus 3, 4, and 0 minus 1, 1. See, multiplying these two matrices. So now what we get, which is equal to, see here, so multiplying first row, first column, 3 into 3, that is 9, plus immediately, minus 3 into 2, that is minus 6, and here 4 into 0, that is 0. First row, first column is multiplied. First row, second column multiplying 3 into minus 3, that is minus 9, immediately plus, minus 3 into minus 3, that is plus 9, and here 4 into minus 1, that is minus 4, so plus minus 4 here, and again first row, third column multiplying 3 into 4, so 3 into 4, third column, that is 12, and again immediately plus, so minus 3 into 4, that is minus 12, this is minus 12, and immediately plus, so 4 into 1, that is 4. So this is a first row, third column multiply. Again second row, first column, 2 into 3, 6, and immediately plus, minus 3 into 2, that is minus 6, and here plus 4 into 0, 0. Again second row, second column, 2 into minus 3, that is minus 6, and minus 3 into minus 3, that is plus 9, immediately plus, and this is also plus 9, and minus 4 into minus 1, that is minus 4 again, so plus minus 4. Again second row, third column, 2 into 4, that is 8, and here immediately plus, so minus 3 into 4, that is minus 12, this is minus 12, and immediately plus, so 4 into 1, that is 4, this is minus here, this is minus. So again third row, first column multiplying 0 into 3, that is 0, and immediately plus, minus 1 into 2, that is minus 2, and plus 1 into 0, that is 0. Again third row, second column multiplying 0 into minus 3, that is 0, and immediately plus, minus 1 into minus 3, that is 3 here, so immediately plus, and here 1 into minus 1, that is minus 1. So next again third row, third column multiplying 0 into 4, that is 0, and here plus immediately, so minus 1 into 4, that is minus 4, this is minus 4, and plus 1 into 1, that is 1, immediately plus 1. See, now we have to simplify this is. We have to simplify. So that is 9 minus 6. So this is A square is equal to, so 9 minus 6, that is 3, and plus 9 minus 9 gets cancelled here, minus 4, and here 12 plus 12 minus 12 gets cancelled, 4, and here plus 6 minus 6 gets cancelled, that is 0. Here minus 6 minus 4 minus 10, and plus 9, that is minus 1. and here plus 6, 12, 8 plus 4 is plus 12, minus 12 gets cancelled, that is 0. And here this is a minus 2, and here 3 minus 1, that is plus 2. So here minus 1 plus minus 4 plus 1, that is minus 3. So simplified a square. See, what we have to show that a inverse is equal to a cube. But here we have a square. Now what to do that a cube is equal to, we have to find a cube. A cube is equal to, find the a cube, what I am doing is here, finding a power 4. Finding a power 4 is how much? Now first we have to find the a power 4. As per that we get a cube also. Find a power 4 here. So a square already we have 3 minus 4, 4. And 0 minus 1, 0 minus 2, 2 minus 3. Again multiplying with a square. So with the same matrix 3 minus 4, 4, 0 minus 1, 0, minus 2, 2 minus 3. Actually what we have to prove, a inverse is equal to a cube. So now I am finding in the alternate method a to the power of 4. What we get, we'll see that. So again first row, first column multiplying. 3 into 3, that is 9. And immediately plus minus 4 into 0, that is 0, and plus 4 into minus 2, that is plus minus 8. Again first row second column multiplying here, 3 into minus 4, that is minus 12, and immediately plus minus 4 into minus 1, that is 4, and plus 4 into 2, that is 8. So again same first row third column multiplying here, 3 into 4, that is 12, and plus minus 4 into 0, that is 0, and plus 4 into minus 3, that is minus 12. This is minus 12. So again, so the second row, first column multiplying 0 into 3, that is 0, and immediately plus minus 1 into 0, that is 0, and plus 0 into minus 2, that is 0. Again second row, second column multiplying 0 into minus 4, 0, and immediately plus minus 1 into minus 1, that is plus 1, and 0 into 2, that is 0. Again second row third column multiplying 0 into 4, that is 0, and plus minus 1 into 0, that is 0, and plus 0 into minus 3, that is also plus 0. Now third row first column multiplying minus 2 into 3, that is minus 6, and plus 2 into 0 immediately, that is 0, and plus 3 into minus 3 into minus 2, that is again plus 6. Now again third row second column multiplying minus 2 into 4, minus 4, that is 8, and plus 2 into minus 1, that is minus 2, and plus minus 3 into 2, that is minus 6. Again third row third column multiplying minus 2 into 4, that is minus 8, and plus 2 into 0, that is 0, and plus minus 3 into 3, that is 9. See, observe here, we get which is equal to, that is a power 4 is equal to, we are getting here 9 minus 8, after simplifying this is 1, and plus 12 minus 12 gets cancelled, this is 0, and plus 12 minus 12 gets cancelled, this is also 0, and here this is 0, and here this is 1, again here 0. So now plus 6 minus 6 gets cancelled, this is 0, and plus 8 minus 8 here. So these two are also gets cancelled, that is 0, and minus 8 plus 9, that is 1. See what we get here, a power 4 is equal to, we get the unit matrix of order 3, that is I. So now we get a power 4 is equal to I here. Actually what we have to prove, a inverse is equal to a cube. So now here this implies, so a power 4 is writing as a into a cube. Can we write now? A power 1 plus 3. So that is a power 4 only, which is equal to I. Now to get the required thing, what I am doing is multiplying by a inverse on both sides. When you multiply by a inverse on both sides, the above condition, it becomes a inverse into A into A cube, so which is equal to I into A inverse. I into A inverse. See here, so now further what I am doing is, here considering A inverse into A, these two matrices product as one matrix into A power 3 is equal to I into A inverse. See, we have the properties clearly here. What are the properties we have? So we have the properties are, suppose A into A inverse is equal to A inverse into A is equal to unit matrix I. So any matrix, if you multiply with the inverse matrix, you get unit matrix only. And also suppose any matrix, if you multiply with unit matrix, you get the same matrix only. Using these two properties, here this is I, A into A inverse is I into A cube, so which is equal to I into A inverse. Using the second property here, A into I is equal to I into A is equal to A we are getting. Similarly, A cube into I and A inverse into I, also what we get? We get this is A cube and this is A inverse. So therefore clearly, so A inverse is equal to A cube. So that's why this problem very easily we can prove that by using this alternative method. In this video we are going to discuss matrices, SAQs, exercise 3, section 1. Fifth problem, if ABC is not is equal to 0, find the inverse of the matrix. See, it is also very important. Now how can you find the inverse of this matrix? See here, so given that let A is equal to taking the given matrix. So this is a diagonal matrix A 0 0 0 B 0. So 0 0 C. First what you have to find the inverse? To find the inverse, first you have to find the determinant of A. So now that A is equal to determinant of, so A 0 0, so 0 B 0, so 0 0 C. So now we get the determinant of A is A into, so this is B 0 0 C and minus 0 into here plus minus plus. So minus 0 into we get, so 0 0 0 C. And here plus 0 into we get, so 0 B 0 0. When you eliminate the 0 presenting row and 0 presenting column, we get 0 B 0 0. Like that remaining also. See what we get here, A into, so this is BC minus 0. So this is completely 0. So that's why finally we get determinant of this matrix A is ABC. But what is given there, determinant of A? Determinant of A is equal to, here we have ABC, but which is not is equal to 0 only. Why? Because here given determinant of A, that means ABC is not is equal to 0. ABC is not is equal to 0. So that's why determinant of A is equal to we get, so ABC. Now what we have to do here? To find the inverse of this matrix A, we have to find the cofactor matrix of A. So now cofactor matrix of A, how to find here? So cofactor matrix of A is equal to here, cofactor matrix of A, so which is equal to, so see here, so we have to find the cofactors of all the elements. So that means here, so determinant of first element is plus, so determinant of here, so A presenting row and column, if you delete we get B 0 0 C, and immediately, so next which is with minus, determinant of 0 presenting column and row, if you delete we get 0 0 0 C, and again with plus determinant of, so here 0 presenting column, row, if you delete you get 0 B 0 0. Again now you have to take with minus, determinant of this is second row, 0 presenting row and column, first column, if you delete 0 0 0 C, we get 0 0 0 C, and again second row, here you get with plus. So now here second row, second column, if you delete A 0 0 C, we get A0, 0, C we get. And here with minus, determinant of here, second row, third column, if you delete A0, 0, 0 we get. A0, 0, 0 we get. And again with plus, so determinant of here, third row and first column, if you delete, we get 0, 0 and B0 here. So next thing with minus, so determinant of here, third row, second column, if you delete, we get A0, 0, 0, A0, 0, 0 and with plus. So determinant of third row, third column, if you delete, we get A0, 0, B only. See, we get the cofactor matrix of A is equal to cofactor matrix of A is equal to, we get here, see this is BC and here 0 and here clearly 0. So that's why this is BC 0, 0. If you observe here, this is 0 and here AC, here 0. So 0, AC, 0 and again here 0 and this is also 0, we get AB. So 0, 0, AB we get. So this is cofactor matrix of A. So but what is adjoint of A? Adjoint of A is equal to cofactor matrix of A transpose. Cofactor matrix of A transpose. Transpose of cofactor matrix of A is called adjoint. Now adjoint we can write it as this is transpose of BC 0, 0, 0, AC 0 and 0, 0, AB. This is cofactor matrix. So transpose also you get diagonal matrix, transpose also you get the same matrix only, see here, which is equal to, so this is BC and first row writing as first column, second row writing as second column, third row writing as third column. So that's why you can observe here transpose of diagonal matrix is also we get same matrix only. So now to find the A inverse of this matrix, which is equal to, the formula is adjoint of A by det A. Adjoint of A by det A. This can be written as 1 by determinant of A. So into adjoint of A is also, now A inverse is equal to 1 by determinant of A is ABC we have, and here adjoint matrix is BC 0, 0 and 0 AC 0, 0, 0 AB. So we get here, finally this is BC by ABC. So 1 by ABC into BC. So BC gets cancelled, we get 1 by A. And 1 by ABC into 0, that is 0. 1 by ABC into 0, this is 0. And again 0 into 1 by ABC, that is 0. And AC into 1 by ABC, we get here 1 by B. So, and 0 into 1 by ABC, we get 0. And 0 into 1 by ABC, that is 0. 0 into 1 by ABC, that is 0. And AB into 1 by ABC, AB gets cancelled, we get 1 by C. See, like this we get, so therefore A inverse is equal to, so this is 1 by A, 0, 0, 0, 1 by B, 0, 0, 0, 1 by C. So like this we can find the inverse of the given matrix. In this video we are going to discuss matrices, SAQs, page number 89, example 1. Very important, many times repeated in the examination. Show that determinant of 1a square, 1b square, 1c c square, which is equal to a minus b into b minus c into c minus e. See how to prove that. Taking the given determinant here, given that determinant of 1a square, 1b square, 1c c square. See here, if you observe that the first column elements are equal to 1, so now you can apply all the elements are equal to 1 only in the first column elements. So you can apply the row transformations. This is R1 here, and this is R2, and this is R3. Now what I am doing is here, R1 writing in the place of R1 and R1 to R1 minus R2. Now first I am doing here, so R1 to R1 minus R2. I am subtracting R2 from R1, writing in the place of R1. So here A minus B, this is A square minus B square. And similarly here R2 to R2 minus R3. So that means, so writing in the place of R2, subtracting R3 from R2. That means 1 minus 1. Here B minus C. So this is B square minus C square. And last row R3 row writing as it is. So now what happens here? So which is equal to here we get, so which is equal to, see 1 minus 1 we know that 0, determinant of this is 0, and A minus B writing as it is, and A square minus B square. See, we know that the formula for A square minus B square is equal to A minus B into A plus B. A minus B into A plus B. So similarly 1 minus 1 is 0 and B minus C here. So now again B square minus C square formula is also, so like B minus C into B plus C we can write. See, we have here the last row writing as it is 1C C square. See here, if you observe that we have the formula for A square minus B square, so which is equal to A minus B into A plus B, which is equal to A minus B into A plus B. Similarly, here also applied that B square minus C square also by using the same formula. So we can write it as B minus C into B plus C. So that's why I applied here for B square minus C square is also B minus C into B plus. Now what I am doing, if you observe that this is now R1 row is this is, and R2 is this is, and R3 is this is. What I am doing is, so taking A minus B and B minus C common, taking common from R2 or from R1. From R1 we have the A minus B. So that's why from R1 and R2. From R1 and R2. See, in the R2 we have A minus B is common. In the R1 we have A minus B is common. In the R2 we have B minus C is common. So that's why here, so in the R1 if you take A minus B common, see what we get here, 0. Here after taking the A minus B common 1 and A minus B common here 1 into A plus B, that is A plus B only we get. And again here after taking the B minus C common from the R2, we get here 0 and this is 1. Here 1 into B plus C, that is B plus C we get. And last row I am not changing anything, writing the last row is as it is only. See, observe here, once after converting the, so in the column elements, first column elements, any two ones as zeros, now you can expand the determinant. Now expanding determinant along so R1, along R1, see here. Now if you expand the determinant along R1, see here. So if you expand the determinant along C1, this is not R1, it's C1. See here, this is first column, no? So that's why expanding the determinant along C1, this is C1, this is R1, so this is R2, this is R3. Now expanding determinant along C1, so C1 deleting and R3 is also deleting. So we get here A minus B into B minus C into here last element along, expanding the determinant along C1 only, no, last element is what? 1. So 1 presenting row and column if you delete, we get the determinant of 1 here A plus B and 1 B plus C. See, along the C1, if you expand the determinant, we get here 1 into the 2 by 2 matrix is 1 A plus B, 1 B plus C. So now which is equal to A minus B into B minus C. Now if you find the determinant of this 2 by 2 matrix, we get here B plus C, B plus C, immediately minus. So that's why multiply with minus. So then minus A minus B, this is A. So finally we get BB gets cancelled. So we get here A minus B into B minus C into C minus C. So that's why this is only the RHS. Suppose if you take the given that LHS determinant of 1A square, 1B, B square, 1C, C square, we get RHS is A minus B into B minus C into C minus A. This is the RHS. So therefore LHS is equal to RHS. So like this we can prove this is very, very important problem. In this video we are going to discuss matrices SAQs, exercise 3D, section 2, second problem. Show that determinant of B plus C, C plus A plus B, and A plus B, B plus C, C plus A, and last row is ABC. See here, we have to prove that which is equal to AQ plus BQ plus CQ minus 3ABs. Now what I am doing is taking the LHS. The LHS is we have here B plus C, C plus A plus B, A plus B, B plus C, C plus A, and A, B, C we have. So now what I am doing is here. So now R12, this is R1, we know that R1, this is R2, this is R3. So now what I am doing is here. So R1 plus R3 I am doing in the first case. So R1 plus R3 writing in the place of R1. So now we get here A plus B plus C here, and here. So also here C plus A we have and B both are adding, then we get A plus B plus C. Here already A plus B is there, in the R3 we have C. So that's why we get here A plus B plus C. So and this second row here, this second row writing as it is A plus B, A plus B, B plus C, C plus A, and third row is writing also as it is A, B, C. So now next what I am doing is here. So this is equal to here R12, R1 minus R2 I am doing again. See here R1 minus R2. So then what happens here? Already A plus B plus C and minus R2 means we get minus A minus B. And again here, so we have A plus B plus C, again minus R2, that is minus B minus C we get, and already we have A plus B plus C minus R2, that is minus C minus A we have. So then again here I am doing in the same determinant R2 to R2 minus R3 also. So the writing in the place of R2 and subtracting R3 from R2. So we get here A plus B minus A, and here B plus C minus B, and C plus A minus C, and here A, B, C. Now what happens here? See here plus A minus A plus B minus B, here minus B plus C minus C, and here plus C minus C plus A minus A gets cancelled. And in the second row also plus A minus A and plus B minus B, here plus C minus C is also gets cancelled. So now we get a 3 by 3 determinant. So which is in the first row we have C, and in the first row we have C, and here we have A, and here we have B. In the second row we have B, C, A. In the second row we have B, C, A. And in the third row we have A, B, C. Now expanding the determinant. So along the first row, that means C into here, C presenting here plus minus plus, if you consider like that. So we get CA, BC, and again minus A into determinant of A present in column row deleted BA we get BA and again here plus B into last element B present in column row deleted we get BCAB here BCAB. Then if you expand it is C into this is we get C square minus AB and here minus A into this is BC minus A square and here plus B into we get B square minus AC. See, observe here clearly if you multiply with this so 2 we get C cube minus ABC and here minus ABC minus into minus is plus A cube and plus B into B square that is B cube plus B into minus AC that is minus ABC we get. See, observe clearly we have plus A cube plus B cube plus C cube. So that's why A cube plus B cube plus C cube and 3 times we have minus ABC here. So that's why we can write this is minus 3ABC which is equal to RHS. So like this we can prove LHS is equal to RHS. So that's why this is very important problem many times repeated in the examination. In this video we are going to discuss matrices, SAQs. Question is page number 71, example 4, very important. Many times repeated in the examination also. If matrix A is equal to cos theta, sin theta, minus sin theta, cos theta, then show that for all positive integers n, a to the power of n is equal to cos n theta, sin n theta, minus sin n theta, cos n theta. See, we can prove these type of problems in the matrices by using the mathematical induction. See, we know that mathematical induction we can prove by using the 3 steps. See, in the solution, first what we have to take? First you have to take that given matrix. So given that matrix A is equal to cos theta, sin theta, minus sin theta, cos theta. See, this is a 2 by 2 matrix, right? So now again what you have to do? So this can be proved, I already told you, by using the mathematical induction. So what you have to do now, first let S of n be the statement. S of n be the statement. S of n be the statement that, what is the statement? So here the matrix A power n is equal to cos n theta, sin n theta, minus sin n theta, cos n theta. This is the S of n. So A power n is equal to matrix cos n theta, sin n theta, minus sin n theta, minus sin n theta, cos n theta here. So this is S of n. Now I already told you it is we can prove by using the mathematical induction. So in the mathematical induction, now I am taking step 1. So step 1. In the step 1, what we do? So put n is equal to 1. So where you have to put n is equal to 1? In the S of n. So what is S of n here? A power n. So now S of 1 is equal to a to the power of 1 is equal to, in the A power n matrix, n replaced by 1, cos 1 into theta, sin 1 into theta, minus sin 1 into theta, again cos 1 into theta. N is replaced by theta. So now what happens here? So if you observe that we get this is the same matrix, A is equal to, so cos theta, sin theta, minus sin theta, cos theta. See, we get the same matrix only here, matrix A. So that's why in the statement, so in the step 1, after taking the n is equal to 1, we get the same matrix. Now we can say that, so S of 1 is true. So it means that the given statement is also true for n is equal to 1. The statement is true for n is equal to 1. Now in the step 2 what we have to do? In the step 2 assume that the statement that is S of n is true for some n is equal to k. But what is k here? N is equal to k. K belongs to the integers. K belongs to positive integers here. K belongs to z plus. Z plus represents the positive integers. So what we have to do now in the step 2? So the meaning of this is S of k is equal to the matrix A to the power of k is equal to so replace n by k in the A to the power of n matrix. So now cos k theta sin k theta minus sin k theta so cos k theta. Now actually we assumed that the statement is true for n is equal to k also. Then finally in the step 3, so in the step 3 what we have to prove that? We have to prove that the statement S of n is also true for n is equal to k plus 1. See, what is the mathematical induction says that the given statement is, we have to prove that in the step 1 it is true for n is equal to 1. In the step 2 we have to assume that the statement is true for n is equal to k. And in the step 3 we have to prove that the same statement S of n is also true for n is equal to k plus 1. Prove that in the step 3 the statement is also true for n is equal to k plus 1. Now you consider a to the power of k plus 1. See, a to the power of k plus 1 is equal to, we can write it as a to the power of k into a to the power of 1. See, a to the power of k plus 1 we can write it as, like we have the property a to the power of m plus n, so which is equal to, can be written as a to the power of m into a to the power of n. So as per that property we can write it as a to the power of k plus 1 is equal to a to the power of k into a to the power of 1. See here, which is equal to a to the power of k, we have the matrix A, and a to the power of 1 is also the matrix A. So both we have to multiply here. So which is equal to, we have the a to the power of k matrix is cos k theta sin k theta. Already we considered in the step 2. So this is minus sin k theta cos k theta, we have a to the power of k matrix into the matrix A is, we have cos theta sin theta minus sin theta here in the second row, so cos theta. So we have to multiply both the matrices to prove that the statement is also true for n is equal to k plus 1, now which is equal to here. So this is multiplying. See, observe here, first row, first column multiplying, both are 2 by 2 matrices only. Number of columns in the first matrix is equal to the number of rows in the second matrix. Resultant matrix order is also, we get 2 by 2. So that's why here multiplying first row, first column. So cos k theta into first column in the second matrix cos theta, and immediately put the sign plus sin k theta here, sin k theta into, this is minus sin theta, again same first row second column multiplying in the next matrix. See, we get here cos k theta into, in the second column we have sin theta, and immediately you keep the sign plus. So sin k theta into, so here we have cos theta. Similarly, now multiply the second row, first column. Second row in the first matrix. So first column in the second matrix, this is minus sine k theta into cos theta. So plus immediately, and cos k theta here, cos k theta into minus sine theta. So now second row, second column in the next matrix, minus sine k theta into sine theta plus cos k theta into cos theta. See, now we get like this one. So what I am doing is here, so removing the brackets, multiplying, this is cos k theta into cos theta, and here plus into minus is minus sine k theta into sine theta, and here we get cos k theta into sine theta, cos k theta into sine theta, and plus sine k theta into cos theta, and here we get both are the minus only here. Here minus also there, here also minus is there. So taking minus common, then here writing it, this is first cos k theta into sine theta, and it becomes also plus sine k theta into cos theta, and here this positive term first writing here, cos k theta into cos theta minus sin k theta into sin theta. See, observe here. So we have two formulas exist here. So suppose if you take cos theta, cos k theta is A and theta is B. So we get here this in this matrix. So first row, first column, in the second row, last element, for both exists the same formula only. That is, we have here cos A plus B, that means cos A cos B minus sin A sin B, which is equal to, we have the cos of A plus B, we have formula, and here first row second element, and in the second row first element. So for both exists the same formula, that is, if you take the cos k theta is A and theta is B, here this is A and this is B, we get sin A here, sin A cos B, and plus cos A sin B, we get cos A sin B, which is equal to, so this is sin of A plus B. This is sin of A plus B. So that's why which is equal to, we get here. So cos A cos B minus sin A sin B, we get cos of A plus B, that is cos k theta plus theta. And here also sin A, k theta is A and theta is B here. So that's why this is sin A cos B plus cos A sin B, we get sin of A plus B, that is k theta plus theta. Again here minus, as it is minus of A. So we get here cos A, otherwise sin A cos B plus cos A sin B here. Sin A cos B plus cos A sin B. We can write it as sin of A plus B, that is sin of k theta plus theta. And here when you take cos theta is A and theta is B here, cos A cos B minus sin A sin B, we get cos of A plus B, that is cos of k theta plus theta. Further it is now in the S of k plus 1, that is we consider A power k plus 1. After taking the theta common, we have k theta plus theta. If you take the theta common in all the elements, so we get cos of k plus 1 into theta, sin of k plus 1 into theta, and minus sin of k plus 1 into theta. So cos of k plus 1 into theta. See, observe that wherever k is there or wherever n is there, we get that k plus 1. So therefore, after getting like this, we can write that the statement is true for n is equal to k plus 1 also. It is also simply can be written as S of k plus 1 is also true. S of k plus 1 is also true. So therefore, finally we can write that by the principle of finite mathematical induction. So S of n, the given statement S of n is true for all positive integers, n. See, so like this we can hence prove. So that's why the given problem we can prove that by using the mathematical induction by using 3 steps. That is, in the first step 1 we have to prove that the statement is true for n is equal to 1, and in the step 2 we have to prove that we have to assume that the statement is true for n is equal to k, and in the step 3 so we have to prove that the same statement is true for n is equal to k plus 1 also. So we prove like this. So that's why the given problem we can prove by using the mathematical induction. Now B into A transpose, here the matrix B is we have minus 2, minus 1, 4, 2, minus 1, 0. A transpose is 7, minus 1, 5, minus 2, 2, 3. Here this is 3 by 2 matrix, and again here this is 2 by 3 matrix. So resultant matrix is also we get. So resultant matrix columns is equal to the rows here. Resultant matrix order is 3 by 3 we get. So that's why which is equal to, now first row, first column multiplying minus 2 into 7, that is minus 14. So minus 1 into minus 2, that is plus 2. Now first row, second column multiplying minus 2 into minus 1, 2. And here second minus 1 into 2, that is minus 2 plus minus 2. Again first row, third column multiplying, that is minus 2 into minus 5, that is minus 10. And plus minus 1 into 3, that is minus 3. Again here second row, first column multiplying 4 into 7, that is 28. And plus minus 2 into 2, that is minus 4 here. We get minus 4. 4 into minus 1, that is minus 4. Second row, second column multiplying 4 into minus 1, minus 4. Plus 2 into 2, that is 4. Again second row, third column multiplying 4 into 5 is 20. And plus 2 into 3 is 6. So third row, first column multiplying minus 1 into 7, that is minus 7. And plus 0 into 2, that is minus 2, that is 0 only. So third row, second column multiplying minus 1 into minus 1, that is plus 1. And 0 into 2, that is 0. So here third row, third column multiplying minus 1 into 5, that is minus 5. Plus 0 into 3, that is 0. See, finally we get here minus 12. And here plus 2 minus 2 gets cancelled, 0. And minus 10 minus 3, that is minus 13. And 28 minus 4, that is 24. And here plus 4 minus 4 gets cancelled, 0. 20 plus 6, that is 26. And minus 7 plus 0, minus 7. 1 plus 0, that is 1. Minus 5 plus 0, minus 5. See, like this B into A transpose also we get. So like this we can prove that A into B transpose and B into A transpose. In this video we are going to discuss matrices, SAQs. Page number 72, example 5, very important problem. If A is equal to matrix 1, 2, 2, 2, 1, 2, 2, 2, 1, then show that A square minus 4A minus 5Y is equal to O. Now in the solution, taking the given matrix, given that capital A is equal to matrix 1, 2, 2, 2, 1, 2, 2, 2, 1. So now first we have to show that the value of A square minus 4A minus 5Y is equal to 0. Finding A square. That means multiplying the matrix A 2 times, A into A. So which is equal to matrix A is we have 1, 2, 2, 2, 1, 2, 2, 2, 1. So into again the same matrix taking here 1, 2, 2. So 2, 1, 2. So 2, 2, 1. See here, multiplying this is which is equal to, so first row first column multiplying, first row first column, that is 1 into 1 plus 2 into 2, so plus this is 2 into 2, again first row second column multiplying, so 1 into 2 plus 2 into 1, so plus 2 into 2, so again first row third column multiplying, so 1 into 2 plus 2 into 2 plus 2 into 1. So first row, first column, second column, third column multiplied. And again second row, first column, that is 2 into 1 plus 1 into 2 plus 2 into 2. Again second row, second column, that is 2 into 2 plus 1 into 1, so plus 2 into 2. Now second row, third column, that is 2 into 2 plus 1 into 2, so plus 2 into 1. So next, third row, first column, multiplying 2 into 1 plus 2 into 2 plus 1 into 2. Again third row, second column multiplying, that is 2 into 2 plus 2 into 1 plus 1 into 2. So third row, second column is over. Now third row, third column, that is 2 into 2 plus 2 into 2 plus again 1 into 1. See, we can observe that what are the values we are getting here. So which is equal to, so this is 1 plus 4 plus 4, 1 plus 4 plus 4, and again here 2 plus 2 plus 2 plus 2 plus 4, again here, so 2 plus 4 plus 2. So in the second row we get, so 2 plus 4. In the second row this is 4 plus 1 plus 4. Again here in the second row 4 plus 2 plus 2. So again last row we get here 2 plus 4 plus 2. Again here 4 plus 2 plus 2. So this is 4 plus 1. See, finally we get which is equal to here. So this is 9, here 8, here 8, 9, 8, 8. Again 8, 9, 8. So 8, 9, 8. We get 8, 9, 8. Again 8, 8, 9 we get 8, 8, 9. So this is the matrix A square. So but what we have to prove that here, so A square minus 4A minus 5Y is equal to O. So therefore the LHS taking here, so A square minus 4A, so minus 5I, which is equal to, see we have the A square matrix here, 9, 8, 8, and here 8, 9, 8, and here 8, 8, 9, and minus 4 into the matrix A is we have 1, 2, 2, 1, 2, 2, 2, 1, 2, so 2, 2, 1, and minus 5 into the matrix I is also, you have to take the 3 by 3 matrix only, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. So now we get here which is 9, 8, 8, and 8, 9, 8, 8, 8, 9. So writing as it is, and here multiplying this matrix A by 4, we get 4, 8, 8, 8, 4, 8, and here 8, 8, 4 we get, and minus multiplying the unit matrix with 5, so we get 5, 0, 0, 0, 5, 0, 0, 0, 5. So now corresponding elements are in, so subtracting here, see 9 minus 4 minus 5, 9 minus 4 minus 5, 8 minus 8 minus 0, and here 8 minus 8 minus 0, corresponding elements subtracting again here 8 minus 8 minus 0, so 9 minus 4 minus 5, here 8 minus 8 minus 0, and here 8 minus 8, so minus 0. So here 8 minus 8 minus 0, and 9 minus 4, so minus 5 at last. See, if you observe here, so all the elements are gets cancelled. Here we get 0, again here 0, again here plus 8 minus gets cancelled 0, so 8 minus 8 is 0, again 9 minus 9 is 0, again 8 minus 8 is 0. See here again 8 minus 8 gets cancelled 0, and here 8 minus 8 0. So finally 9 minus 9, so this is also 0. It is a null matrix, it is denoted by O. So therefore like that A square minus 4A minus 5I is equal to O we can prove. So in this video we are going to discuss matrices, SAQs. So page number 76, 3.3.4 example. So if matrix A is equal to 2 minus 1 2, 1 3 minus 4, and B is equal to 1 minus 2 minus 3 0, 5 4, then verify that AB whole transpose is equal to B transpose into A transpose. In the solution, so given that matrix A is equal to, so 2 minus 1 2, 1 3 minus 4. So now this is a 2 by 3 matrix, and similarly matrix B is equal to, so we have 1 minus 2 minus 3 0, 5 4. So this is 3 by 2 matrix. See here, number of columns in the first matrix A is equal to the number of rows in the second matrix B. So that's why matrix multiplication is possible, and also the resultant matrix, that means AB we get. So AB we get 2 by 2 matrix. So that is A, matrix A is 2 minus 1 2 and 1 3 minus 4. So which is multiplying with the matrix 1 minus 2 minus 3 0, 5 4. So now we get here 2 by 2 matrix. So that's why here, so 2 rows and 2 columns. Now first row, first column multiplying and writing in the first row. That means first row, first column writing. So that's why this is 2 into 1. So plus minus 1 into minus 3 and plus 2 into 5. So this is first row, first column I multiplied. And again first row, second column multiplying and writing in the first row, second column place. That is 2 into minus 2. This is 2 into minus 2 plus minus 1 into 0. Minus 1 into 0 plus. So this is 2 into 4. 2 into 4. Similarly, second row, first column. Writing in the place of second row, first column. That is 1 into 1 and plus 3 into minus 3. So again here plus minus 4 into, so 5, minus 4 into 5. Again second row, second column multiplying and writing in the place of second row, second column. So 1 into minus 2 and plus 3 into 0, 3 into 0, plus minus 4 into 4, minus 4 into 4, second row, second column. See what we get here, which is equal to, here 2 plus 3 plus 10, and here we get minus 4, so this is minus 0 and plus 8, so this is 1 minus 9, so this is minus 20, so here we get minus 2 plus 0, so minus 16, so which is equal to, we get after simplifying, so this is 2 plus 3 plus 10, so we get 15, so and here 8 minus 4 is 4, and here 1 minus 29, this is a minus 28, and here minus 18 we get, minus 18 we get. This is what AB only. So AB whole transpose, so that means we get, so AB whole transpose is equal to, AB whole transpose is equal to, writing first row into the column. So transpose matrix means interchanging the rows into columns, and second row writing into the second column. So that's why 15 minus 28, 4 minus 18 is the AB whole transpose. Now actually what we have to verify here, B transpose into A transpose. But what is given matrix A is equal to, A is 2 minus 1, 2 minus 1, 2, and here 1, 3 minus 4, 1, 3 minus 4, this is 2 minus 1, 2, and 1, 3 minus 4. So from this A transpose is equal to, we get, see here, first row writing into the first column. So that is 2 minus 1, 2, and second row writing into the second column 1, 3 minus 4. So this is A transpose. And again B we have here, B is equal to, so 1 minus 2, so minus 3, 0, 5, 4. Again transpose of B is equal to, so B transpose is equal to, so first row writing into the first column 1 minus 2, and second row writing into the second column minus 3, 0, and third row writing into the third column 5, 4. So now what we have to do, we have to do that B transpose into A transpose. Now B transpose, so therefore B transpose into A transpose. This is actually RHS. So B transpose into A transpose is equal to, so what we have B transpose here, 1 minus 3, 1 minus 3, 5, and minus 2, 0, 4 into, so the transpose of A, that is 2, 1, minus 1, 3, so 2 minus 4. See, observe here, the matrix B transpose is, so 2 by 3 matrix, and here if you observe that, so 2, 1, minus 3, minus 1, 3, 2, minus 4. This is a 3 by 2 matrix. Again, first matrix columns is equal to the second matrix rows. The resultant matrix order is 2 by 2 only. So now which is equal to here. So multiply the first row, first column. So that is 1 into 2 plus minus 3 into minus 1 and plus 5 into 2, 5 into 2. Again, first row, second column multiplying, writing in the place of first row, second column, 1 into 1 and plus minus 3 into 3, minus 3 into 3 plus 5 into minus 4, 5 into minus 4. Again, second row, first column multiplying here. So minus 2 into 2 and plus 0 into minus 1. So again plus 4 into 2, 4 into 2. Second row, second column multiplying, minus 2 into 1 plus 0 into 3, plus 0 into 3 and plus 4 into minus 4, 4 into minus 4. Finally we get, after simplifying, so this is 2 plus 3 plus 10, 2 plus 3 plus 10. So next here 1 minus 9 minus 20, and here minus 4 and this is minus 0 plus 8. So here minus 2 plus 0 minus 16. So if you observe that here first element is 15, so here second element is minus 28, this is minus 28, and third element is 8 minus 4 is 4, and minus 2 minus 16, that is minus 18. So this is we get RHS. Already we have LHS is equal to here AB whole transpose LHS is equal to 15 minus 28, 4 minus 8. Observe that. You can observe that both are same only. So therefore LHS is equal to RHS we can write. So therefore finally also you can write that. So AB whole transpose is equal to B transpose into A transpose. So like this we can prove. In this video we are going to discuss matrices, SAQs, page number 80, section 2. Third problem, if A is equal to 7 minus 2 minus 1 2 5 3 and B is equal to minus 2 minus 1 4 2 minus 1 0, then find A into B transpose and B into A transpose. See, first what I am doing is taking the given matrix, given that capital A is equal to, we have a, so 7 minus 2 minus 1 2 5 3, and from this finding the A transpose is equal to, we have it. So first row writing into the first column 7 minus 2, So second row writing into the second column minus 1, 2. And third row writing into the third column. So that is 5, 3. And again we have matrix B is equal to, so minus 2, minus 1. So 4, 2, minus 1, 0. So again finding the transpose of B. So B transpose is equal to, so first row writing into the first column minus 2, minus 1. And here 4, 2, second row writing into the second column. And minus 1, 0. So now first finding here, so A into B transpose, which is equal to, see the matrix A is equal to, we have here 7 minus 2 minus 1 2, so 5 3. So this is multiplying with the matrix B transpose, that is minus 2 4 minus 1 minus 1 2 0. So the matrix A order is, here we have 3 by 2, 3 rows and 2 columns. And here we have 2 rows, 3 columns. So the resultant matrix order C we get here. So 3 rows and 3 columns only we get. So which is equal to, we can multiply that. So that is first row, first column multiplying 7 into minus 2, that is minus 14. And plus here minus 2 into minus 1, that is 2. Now second row same here, first row second column multiplying 7 into 4 is 28. And plus here minus 2 into 2, that is minus 4. So same first row third column multiplying here. So 7 into minus 1, that is minus 7. And plus minus 2 into 0, that is minus 0 or plus 0. So here second row first column multiplying minus 1 into minus 2, that is 2. And plus 2 into minus 1, that is minus 2. So here plus minus 2 actually. So and here second row second column multiplying minus 1 into 4, that is minus 4. And plus 2 into 2, that is 4 only here. Again second row third column multiplying minus 1 into minus 1, that is plus 1. And plus 2 into 0, that is 0. Again third row first column multiplying, that is 5 into minus 2, that is minus 10. And plus minus 3 into minus 1, that is minus 3. So here third row second column multiplying 5 into 4, that is 20. And plus 3 into 2, that is 6. Here third row third column multiplying 5 into minus 1, that is minus 5. And plus 3 into 0, 0. So we get finally A into B transpose is minus 14 plus 2, that is minus 12. 28 minus 4, that is 24. So here minus 7. So here 2 minus 2 gets cancelled, 0. And plus 4 minus 4 gets cancelled, 0. And this is 1. So here minus 10 minus 3, that is minus 13. Here 20 plus 6, that is 26. Minus 5 plus 0, this is minus 5. So we get A into B transpose is equal to minus 12, 24, minus 7, 0, 0, 1, minus 13, 26, minus 5. Again we have to find the B into A transpose. So S of k plus 1 is equal to, we have a to the power of k is, the matrix is 1 plus 2k minus 4k, k, 1 minus 2k. And matrix A is 3 minus 4, 1 minus 1. Now multiplying both the matrices here, first row, first column, if you multiply, so 1 plus 2k into 3 and plus minus 4k into 1, and immediately first row, second column, if you multiply 1 plus 2k into minus 4 and plus, so here minus 4k into minus 1, minus 1. So then here, so second row first column multiplying k into 3 plus 1 minus 2k into 1. So here k into my second row second column multiplying k into minus 4 and plus 1 minus 2k into minus 1. 1 minus 2k into minus 1. So now it is equal to, if you multiply that, we get here 3 plus 6k, and plus into minus is minus 4k, and here minus 4 minus 8k, and here minus into minus is plus 4k. So next here 3k, k into 3, and here plus 1 minus 2k. So here minus 4k, and if you multiply with minus, this is minus 1 and plus 2k. See further what we get here. So 3 plus 2k, this is 3 plus 2k, and here minus 4 minus 8k plus 4k, that is minus 4 minus 4k, and here so we get 3k minus 2k, that is k, so we can write k plus 1, and here minus 1 and minus 4k plus 2k, so that is minus 1 minus 2k, this is minus 2k. See, our aim is what? Every term must be, we have to prove in terms of k plus 1. So that's why here, which is equal to, this 3 is writing as 1 plus 2 plus 2k, and here minus 4 is taking common, minus 4 into, we get 1 plus k or k plus 1, both are same. Here k plus 1, and here minus 1 writing as 1 minus 2. See, minus 1 is nothing but 1 minus 2, and minus 2k is writing as it is. So now which is equal to, we get, so here 1 plus, if you take 2 common here, 2 into k plus 1, and here minus 4 into k plus 1, minus 4 into k plus 1, and here k plus 1. So here if you take minus 2 common, we get, so 1 minus 2 into 1 plus k or k plus 1. 1 minus 2 into, so k plus 1. So see, observe here in the S of k, wherever k is there we get the k plus 1. So 1 plus 2 into k plus 1 minus 4 into k plus 1, k plus 1, and 1 minus 2 into k plus 1. So therefore clearly we can write that S of k plus 1 is also true. S of k plus 1 is also true. So therefore by the principle of finite mathematical induction, S of n is true. S of n is true for all positive integer. So n is greater than or equal to 1. So that's why like this we can prove the solution.